All right, welcome back. So this is the last of the four sections on my paper on extensions of hyperfields. So I guess last time we kind of did this construction on sort of how to get strong extensions of quotient hyperfields containing roots to polynomials. And so the goal of this section is to show that if you have an extension of a hyperfield, the minimal extension containing a root is not necessarily unique. That is, if I have a hyperfield K and I have some polynomial without a root in K, and if I have some C is a root of our polynomial little k, then K adjoin C is not well defined. In either case, in either the weak extension or the strong extension case. So if you're just considering weak hyperfield extensions, you still can't make sense of what it means to be minimal. Similar for strong hyperfield extensions, we still don't know what it means to be minimal. And as I hinted in the second part of this series, and the second section of this paper, is the weak hyperfield of signs, which we saw had the quotient structure of taking the field of p elements and modding out by the squares, where p is a prime, where we need p is greater than or equal to 7 and congruent to 3 modulo 4. And let's consider the polynomial over the hyperfield of signs, 1 plus t squared. This has no roots. And the way you see it has no roots, if you plug in 0 in here, you get 1 plus 0, which is 1. If you plug 1 in here, you get 1 plus 1, which is 1 and negative 1. And if you plug negative 1 in here, you get 1 plus 1, which is 1 and negative 1. So this has no roots in W. So our goal is we will consider the extensions. So we will consider W is F7 mod the squares of the field of 7 elements. And this will give us an extension, maybe I will call it L, which is F49 modulo just the squares of F7. So we will consider this as one such extension, and we'll actually prove this is minimal. And then we will take a second quotient structure, and considering F11 mod the squares, and then our corresponding extension will be 121 mod F11 squared. And we'll show this one is minimal in its own right, and we'll also show we don't necessarily, L kind of gets a bit too computationally by hand to do nicely, but we'll just do some group theoretic arguments to saying whatever minimal extension between W and L, if L is minimal, we'll see these aren't isomorphic. But if there were something in between, we'll prove it can't be isomorphic to F49 mod F. F7 squared. So that's sort of the goal. So here's the first theorem, is that our F49 mod our squares is a minimal extension of W containing a root of our polynomial k, and this k is exactly the 1 plus t squared, which we have above. So the proof is as follows. Well, we note by construction, by the construction we saw last time, if I say L, I'll denote L being sort of this field. This contains a root to k by construction. So we'll just have to show it's minimal. And what we'll do is we're going to kind of simplify some notation. So F49, we will think of this as F7 adjoin the element I, where I squared is -1. So that's our first observation. Our next observation is if we consider F7 star squared. So if we consider our squares mod 7, our residues will be 1, 2, and, well, 4. However, I like to do my work with the minimal distance from 0. So instead of 4, 4 and -3 are the same mod 7. So we now know what F49 is. We know what our squares are. So the next part is we just write down all of the equivalence classes. So I'm going to write this down. So the equivalence class of 0, we know this is just 0. The equivalence class of 1, this is going to be our residues. So 1, 2, and -3. The equivalence class of, well, I'll call it -1, is going to be our quadratic non-residues, so -1, -2, and 3. And this is kind of nice because the way we've set things up is because -1 is not a square, you just have these 3 in our hyperfield of signs. So this here constitutes our F7 mod, F7 modulo the squares. And that's why I kind of have written things as 1, 2, and -3 rather than 1, 2, and 4. So our next equivalence class is, well, maybe we can do well, we'll do some counting later. So we have I, so we should get a I, and then, well, it should be everything in our equivalence class, all of our squares multiplied by I. So we get I, 2I, and -3I. Then we will have an equivalence class of -I, which will be -I, -2I, and 3I. And we can continue on the equivalence class of I plus 1, so we need to multiply this by 1, 2, and -3. Then we have an equivalence class of -I plus 1, which will be -I plus 1. Then I have to multiply this by 2. So -2I plus 2, and then multiply it by -3, so this will give me a 3i minus 3. Then I will have my equivalence class of I plus 2, which will be I plus 2, 2i minus 3, and minus 3i plus 1. So multiply by 1, multiply by 2, multiply by -3. Is this correct? Negative 3i plus 1. Because -3 times 2 is 1, yes. So minus I plus 2 will be the exact same thing, but I have to... Wait. No, it won't. It'll be negative I plus 2. Then it'll be minus 2i minus 3, and then 3i plus 1. Again, you just multiply by 2 and then -3, and we can continue on in this way. I will do so here. I'm just looking at the paper where I had worked these all out. So I have I plus 3, and then when I multiply by 2, I should get 2i minus 1. And then when I multiply by minus 3, I should get minus 3i minus 2. Then I have an equivalence class of negative I plus 3, which should be negative I plus 3. I have to multiply this by 2 to get a negative 2i minus 1. And then I have to multiply this by a negative 3, which will give me a 3i minus 9 is the same as minus 2. And then we keep going, and what happens is I will get a I minus 1 minus I minus 1 I minus 2 minus I minus 2 I minus 3 minus I minus 3, and we can fill all of these out and just verify. So I have to multiply this by 1, I then have to multiply it by 2, and then I have to multiply it by negative 3, which should give me a 3 minus 3i. Multiply this by 1, multiply this by 2, multiply this by negative 3, multiply this by 1, multiply this by 2. 2 times negative 2 should give me a 3, so this should be a 2i plus 3, and then I have to multiply this by negative 3, so negative 3i minus 1. Here, multiply by 1, multiply by 2 should give me a negative 2i plus 3. And then multiply by negative 3 should give me, so I should get a 3i minus 1. If I multiply this by 2, I should get a 2i minus 6 is the same as plus 1. And then multiply by negative 3 should give me a negative 3i. So 9 is the same as 2 plus 2. And then here, multiply by 1, multiply by 2, this should be minus 2i plus 1, and then multiply by negative 3, I should just get a 3i plus 2. So, this is our list of every coset representative in the extension that we are looking at. And all we did to create this list was say, well, we have sort of what elements we have in our F7 adjoin I, and we know we have this equivalence relation, so let's just multiply by the elements in our equivalence relation to see what the equivalence classes are. So now we're going to do a counting argument. So let's recall L is F49 modulo the non-zero squares. So this, if we look at F star, so the non-zero elements, there will be how many non-zero elements? So on the one hand, we know this has 49 elements. Let's see. So our size of L star will be 16. And furthermore, we will know, because is there a nice heuristic? Because what we know is we have our 0 element here. So if we take away our 0 element, there are 48 elements remaining. And so there are 3 squares, and then 48 divided by 3 is 16. So that's how we know there are 16 non-zero elements here. And if you count, there are 16 things here, and all the things in these brackets, if I didn't make a typo, should all be the different elements of F7 adjoin I. So we know our L star is going to be the multiplicative group has order 16. Furthermore, what we know is something else. We know the multiplicative group of a finite field. So L star is isomorphic to F49 star modulo F7 modulo these squares. From field theory, we know that the multiplicative group of a finite field is cyclic. And if you quotient out a cyclic field, this tells us that L star isn't just any group of order 16, it is a cyclic group of order 16. So we now have the following. So we will show that this L is indeed the minimal extension. So let's assume we have K is a minimal weak extension of W with a root in K. So what we have here is we know K has to sit between W and L. It's not equal to W because W didn't have any roots, but it's something contained in L. We will show, we claim that our field K is actually equal to L. That is, our minimal weak extension here actually has to be L. And to do this, it suffices to show that the multiplicative groups of K star and L star are the same. So we will have to use Lagrange's theorem here. So by Lagrange, since these are finite groups, we know that the size of K star has to divide 16. So that's our first observation. K star, the size of it has to divide 16. So we're looking at 1, 2, 4, 8, 16. We're going to show it's actually 16. Since we know that it contains W, this implies that the order, that the size of K is at least 3. But since it contains a root, to our little k here, this implies that either I or minus I are in K, because these will be the two elements. If you square all of these elements, one can check I and minus I. These are the only things that square and have -1 still in their set. So we know we have to have one of these as a fourth element. So we have at least 4 elements, but we have both. Since minus I times -1 is equal to I. So, and this is like in the hyperfield setting. So in some sense, kind of multiplication of by -1 tells us we have both of these. So at this point, this tells us we have that the size of K star, we're already up to 5 things. So in some sense, we now have 5 non-zero elements, so we know it's either 8 or 16. We will show it's 16. So let's do this. Since we know L is a... So since we have that 1 and I live in my hyperfield K, if I take their sum, and this is a weak hyperfield extension, which is contained in L. So their hyperfield extension, if I take this sum in K, it has to be a subset of whatever the sum is in L. And we can check just if I add, well, if we recall 1 is equal to the set 1, 2, minus 3, I is the set I, 2i, minus 3i. This 1 plus I set, this should be the set containing, well, I should get a 1 plus I should get a 1 plus 2i, and 1 minus 3i. So I should get a 1 plus I. So that's coming from doing this addition, and that addition. Those will all be 1 plus I elements. You can also get a I plus 2. That's kind of doing this sum here. And you also need an, or wait, is it I plus 2? Oh, I was doing this sum here, and then an I minus 3. And you can go ahead and check that this is actually the sum in L. So this implies that Y, or K, it has to contain at least one of 1 plus I plus 2, and I minus 3. So we can now continue on. We have at least 5 elements. We're either So the size of k star is either 8 or 16. We want to assume it's we want to show it's 16. So if we assume for the sake of contradiction that this size is 8, so this implies that k star contains elements of at least order 8. It contains elements of order, well, at most 8. But then you can continue on playing this game and ask the elements of order 8 will be sort of the following. You'll have your 1, you'll have your -1, so this is your element of order 1, your element of order 2, you'll have your 2 elements of order 4, and then there should be 4 elements of order 8. And this will be kind of your 1 plus I and all the permutations of that sign. So these would have to be all the elements of k star. So, but we're an extension. And if we consider, we have to have I, because that's an element of order at most 8. Let's consider, if we add this to the set 1i plus 1, if you work it out, this is the set, when you work this out in L, is I minus 3, minus I minus 3, minus I plus 2. None of these are in K. But our hypersum has to give us a subset of K, and it has to be non-empty. So we must have another element and we conclude that the size of k star is 16, so k equals L. That is, L is a minimal extension. So this is really much more computational of saying, oh, I know what my thing is, let me just write it down, and let me show, use things we know about groups, namely multiplication groups of finite fields are cyclic, along with Lagrange's theorem to show this, you have to have everything here. So this gives us our minimal extension. So now, here is the next idea. So here's our next theorem. So this is showing that we know we have one minimal extension, namely F49 mod the squares of F7. So the theorem is, if I take my F49 mod my squares of F7, this extension, it is a minimal extension, but it is not contained in kind of as a sub-hyperfield of our other extension that we were considering when we picked our prime to be 11 instead of 7. And this implies minimal extensions containing roots are not unique. That is, we can't, F adjoin a root is not well defined, or K adjoin a root is not well defined for a hyperfield K. So I'm not going to sort of, for this 121 mod the squares, I honestly do not know if this is a minimal extension or not. I'm sure if I had to guess, well, I don't know. I'd imagine it is, but I didn't go through sort of looking at all the cosets, and I did not want to do that. So there's a trick we can do. So let's assume, for sake of contradiction, that we have F121 mod the squares is an extension of F49 mod the squares. So if we look at multiplicative groups, we have to have that the multiplicative group of F49 modulo the squares, so this multiplicative group, is a subgroup of F21 modulo the squares. It's a subgroup of this multiplicative group. So we can now count. We must have that, well, what is the size? By Lagrange's theorem, we have this subgroup relation. The size of F49 mod F7 is 16. So this has to divide, 16 must divide, what is the size of 121 mod the squares of F11? Well, we have 120 elements of F11, or F121, which are non-zero. And then how many squares do we mod out by? We're modding out by 5. So this is going to be, this implies that 16 divides 24. So there are, this group here has 24 elements. And so if we had that F121 mod the squares is an extension of that, this would imply 16 divides 24, a contradiction. So from this, we conclude that this F49 is a minimal extension. And furthermore, whatever minimal extension, I don't know if this is a minimal extension or not, maybe there's something that lies between, but whatever does lie between, it cannot be isomorphic to this F49. And so that allows us to conclude that minimal extensions containing roots over hyperfields are not well defined. And that's kind of the end of this paper. Thank you for listening.